none found. These scan devices. So just let me see whether it is on or not. So, all right. So we have connected your laptop with the data acquisition system, that is Power Lab.
حاول تنتبه أيمن بعد. Okay.
And what we will just do in the first thing is get a signal so that you know what is happening. This is a transducer which is known as pulse transducer. Okay.
Mm-hmm.
So if you just put it like this, what it is going to measure?
The pulse and
So, and you can see here, if you start, this is just press start button here. Okay, start recording, and there should be on channel 3. Let us see what happens. So we are getting some record, but not. And there should be on channel 3. Let us see what happens. So we are getting some record, but not. So there should be a record there, huh? Okay. Which is not very clear. Channel 2. We'll go and see what happens there. We have very noisy signal. This is all noise.
Okay.
When there is a signal which is unwanted type of thing, then we call it noise. Now why there is noise? Sorry. Close this thing. What I have done is I have highlighted an area. Okay.
Yes.
And I go to here, data pad.
Okay.
Press the first icon. It gives you the number of channels which are being displayed here. We are not using all of them. We are using channel 2 only at this time. Okay. So you press on channel 2. It gives you various options. Either you can switch it off, or you can have some statistics, selection, comment, slope, integral, block information, cyclic measurements. This is the thing which we most commonly use, and then later on we will be using HRV also. Okay. So cyclic measurements means there is a signal which is cyclical in nature, repeating at a particular frequency. So we can measure so many things. Everything is automated. So we can select that we want just the rate at this. We want to calculate the heart rate from the pulse. Okay. So we select this one. We have certain options, format, etc. Say we go to options, and we say here this display. We click on to various options. So what was this? This is basically I think you left finger pulse. Okay, the last option is there. The transducer is a finger pulse transducer, so you select this one. Okay. So what is the benefit of this selection? The program in itself has built-in facility that it takes care of so many things that otherwise you will have to do manually. So automatically whenever you put finger pulse transducer, all the relevant settings come into action. Okay. If you were using a respiratory belt, then you would select here respiratory belt. If you were using something else, similar. Okay.
Yes.
Then you can also format, because heart rate you will not have in fractions. Either it will be 67 or it will be 72, not 72.379.
Okay.
So you make the display as a fixed decimal. We don't need any decimal.
Okay.
Okay. And then one small thing also.
The rate, doctor, you how do we do the rate like you did last time?
Average cycle rate. Okay.
Okay.
And then there is an option of mini window so that it can be displayed. So this is mini window on and okay. So this is now coming. Why it is not formatting to 0? Yes. Okay. So finally we give the OK signal, and this is, you immediately get your heart rate. Okay.
Okay.
Now I can just highlight two of them and see heart rate is 90. Okay. I go forward, heart rate is 83. Now this is what I wanted you to understand now. What is happening?
Okay.
Tell me.
We are measuring the heart rate on the interval we choose,
Yes.
and then it will be shown in this mini window if we open it from the what is called the data bar.
Okay. This is the experimental description. Now the actual thing, what you are going to actually do in your whole project
Okay.
is to see how these differences vary. What I have shown you, this interbeat interval, this is interbeat, isn't it? One beat and second beat.
Yes.
Okay. Two successive beats are there.
Yes.
This is called instantaneous heart rate. What? Instantaneous. The heart rate at this particular moment.
Okay.
So at this particular moment, the heart rate is,
90.
at this particular moment it is,
83.
at this particular moment still 83. Here 85. Here 86. 91. 90. You understand what is happening here?
How can we determine the exact start point? Or
That the program itself is doing.
okay.
We have selected that our recording is a finger pulse recording. So all the settings are there that it will just detect a peak. So peak to peak interval are being
Okay.
measured.
So
Okay.
it doesn't matter if we select a little bit before the beat. Or
Yeah, doesn't matter. See, if I select from here till here.
Okay.
Okay.
Okay, so doctor, what's the use of this in our?
This is what is heart rate variability.
Okay.
Okay.
I understand that, but I mean, يعني, they asked which point did we start? So any point,
No,
and
then
compare
you-
it to what?
Then, yes, then you will have to follow a protocol that this is the interval you will select, this long interval you will select. For all practical purposes, the international recommendations are that whenever you are doing heart rate variability, you should have a 5-minute segment. 5 minute, not 5 beats. 5 minutes means 300 seconds. Okay.
Okay.
There are certain situations where you can have smaller segments also, but as a standard rule, remember, we should have a stable record of how many minutes?
5 minutes.
5 minutes. Okay. How many seconds?
300.
300 seconds. That should be equivalent to approximately 300 beats.
Up 60 beats per minute.
So if you don't have 300 beats in your record, then this record may not be acceptable.
So we are looking for the time or the beats.
Basically
Which
time.
minimum?
Time.
Hmm.
5 minutes.
But even if the person who's testing has a lower heart rate.
In the article you will have to write 5 minutes.
Mhm.
But practically sometimes even 4 minutes, 3.5 minutes, we can be sure that yes, the data is okay.
It's consistent.
Okay? Yeah.
Consistent.
All right. That was the basic thing to understand that this is your objective, heart rate variability. We do not calculate heart rate variability from the pulse. This is not the standard thing. The standard thing is to take ECG recording. Okay? Because this pulse is not having a sharp peak. See, if you go back to datapad and go to options, see the program is just marking the beats. You can see these small circles on every beat. Okay? So it may be different by some milliseconds if we compare it with the ECG. Now our next job is to record ECG. Yeah. But the thing what I just want you to keep in mind is that pulse rate is our backup. Sometimes the ECG record just becomes noisy, so noisy that we cannot calculate. So we have a backup of the pulse.
Okay.
We will have still another backup when we start recording the finger arterial blood pressure with this other machine. That will be our third signal. So we will have 3 options. Of course, basically it should be done with ECG. If ECG record for some reason is not suitable, then we could go to the pulse. If that is not suitable, we could go even to arterial blood pressure signal. Okay? All of them will give us approximately the same result.
The most accurate is the ECG.
Yes, accurate, and this is the standard. Okay?
Okay.
Because rest of the waves are sort of, they will not give you a very sharp peak. So there could be a difference of some milliseconds here and there. All right. So okay. Now you see you have got HRV here at top.
Okay.
So how we can do HRV analysis is just an introduction, so you will have a little idea. I am just selecting a very short segment just for demonstration. It should be a 5-minute segment.
How long is this segment?
Let us see. This is starting from 50 approximately and going to 58. So about 7.5 seconds only. We can see if it is a stable record, we can increase. Yeah, it is a stable record. We will just have a bigger one starting from here till here. So now it is starting from 35 to 135, about a minute now. Okay. So we go to HRV panel. There are 5 things here. Number 1 is settings. We go to settings. So all the things are default. Now the default setting is that it is probably wanting to calculate the HRV from channel 1, whereas our record is on channel 2, isn't it?
Yes.
So we change this one to channel 2. Then default setting is whole channel. No, we just want our selection. Rest of the things we will not tamper with. There is one important thing is exclude ectopics from analysis. What is an ectopic?
An extreme.
Hmm?
An extreme value.
Not an extreme value.
Artifact?
The exogenous or the
Yeah.
external.
Yeah, out of place it is ectopic. A normal beat is coming from SN node, isn't it?
Yes.
You remember SNO?
Yes, of course.
Now, as you had mentioned, an artifact, if you just touch with a finger, there will be a signal there. And if that signal is included in the calculations, your readings will not be correct. Rather, we should say it will be invalid.
Okay.
And I will demonstrate it to you also. So, usually we exclude ectopics from analysis so that our analysis becomes good, then okay. So, it is detecting these beats. All circles are there. And now immediately you can see that it has missed this one, it has missed this beat, it has missed this beat. So many beats are not being detected by the program at certain thresholds. So we can go back to settings, and the main thing which we can change we will have to go to custom, okay, because this is not an ECG record, that's why the program is confused. So now we are going to do it ourselves. We go to advanced, and here you see standard deviation. The program has got an ability that it calculates the heights of these peaks. Okay, so the average height is whatever. So in comparison to those heights, if anything is smaller than that, it misses. Okay, so this is statistical thing basically. Now what we are going to do is we will reduce the SD, and you see that
More circles.
More circles are there. Okay, we have reduced it to 2, and let us see what happens. Now all of them are detected.
Yes,
Isn't it?
there's one that isn't, I think.
This one, huh?
Yeah.
So what is happening here? You visually see we have reduced it to an extent where this is an artifact. Let us just see. We can zoom this area. See what is happening. So this is a zoom view. So what is happening? It is marking this one, this one, this one, and then this small one is also been marked. Means we have reduced the SD a bit too much, isn't it? But rest of them are okay. Now how to overcome this problem? The time interval between these two successive beats is, we can calculate. See, there is a marker option here, isn't it? You put a marker on one beat and go to the next, and see the time interval between two is 629.629 second. Okay,
Between the two beats.
yes, means something around 0.7 of a second,
Okay.
or 700 millisecond, whatever you want to say. So the other option now, very simple, straightforward, is we go back to settings again, go to advanced again, and see here they have put minimum of 300 milliseconds, isn't it?
Yes.
So if we increase it to say 550, probably will be safe. Okay, okay. Let us see. Yeah. Now it will not mark another peak which is less than your defined time interval.
Okay.
So now you are more likely to get to every successive normal beat.
So should we fix it if we had another accident like we just did, and have and make it so that there's a dot or a circle above every beat, or is it
Yes.
okay to ignore one of them?
No, we cannot ignore.
All of them? Huh? We can't consider that one an artifact or.
The program itself will have certain safeguards, yes.
Okay,
But
so-
we try to get the whole data.
Okay.
Okay. So now we have completed this whole thing. This 1 minute segment, all of them are identified. There is nothing which we can call as an artifact. All these are regular heartbeats. There is the next another thing which is called beat classifier. We use this beat classifier.
Can you give us a minute, doctor?
Use this extension wire, huh? If you want.
I have one.
Okay, adapter you have? Okay. All right. Huh? So what we can do next is a beat classifier. This also would help us in actually achieving the same objective which we have done through settings. Okay. Okay. So beat classifier, it is showing all the beats.
I didn't bring it. Where's the adapter?
Okay. But take care, huh? Your mobile should not be trampled down your feet.
Okay.
Put it in this trolley. Huh? So what this software is doing, it is giving us all the beats here which we have outlined in this particular area, spanning from about 610 millisecond to 760 millisecond. Okay, so these all crosses they are basically. So if we now, this is a frame that will include all these into calculations. Now their color has changed. All of them are blue. Blue here means all beats we have okayed. They are correct. Only it will be blue if this whole square or rectangle, I should say rectangle, is encompassing all these beats. Now we will give a command.
No, there is a.
Haha. Let us include this one also.
This will be an interesting
Yeah.
point.
Okay.
Because this can happen to them.
Now the third panel is report. This is your report, your results which you want for HRV. You are not doing anything manually. I will go through the manual process also once you understand a little bit of. So analysis start, it will give you that we are starting at 35.2 second. Okay, this is 35.2. Analysis end is 133.75. So it's a 1 minute step. Total included beats 86, all normal, no ectopic. Okay, this is reassurance for you, your data will be valid. Then average RR interval, peak to peak interval. As I mentioned that there was a difference of 0.697 second. So the average RR interval here, it has calculated 666 milliseconds. Okay, median is 664. Now rest of these are statistical calculations. The program is doing by itself. SDRR. SD, you understand standard deviation.
Yes.
Standard deviation is
The bell
The
curve.
deviation
it's-
from the media.
it's from the median. Some of them are plus, some of them are minus. So standard deviation of RR interval on an average in this 1 minute segment is 30.23 milliseconds. This is a very important parameter that is usually stated in your articles, that what was the SDRR or SDNN. This gives you an idea of overall variability of your pulse. The greater the variability, the better it is. Okay?
Okay, in 1%. That is.
Yeah, in one person. That is the usual case in a normal person. If my heart rate is too fast, so you will not see much variability. My heart is slower, you will see greater variability. So it is heart rate dependent.
So
Okay.
the bell curve should be flatter.
Yes, you can say. There are certain normal limits. Too much is also bad. Khairul amuri.
Also,
Okay, so there will be a range. Beyond that or below that, you have to see. Okay. So this is standard deviation of RR intervals. Then there is a coefficient of variation of RR intervals. We usually don't go into this one. I have not used it up till now in any article. Average rate would be inverse of average RR interval. Rate and interval would be reciprocal of each other. So heart rate was at this 90 beats per minute. Then we go to this RMSSD, again a statistical thing. It is usually close to whatever you do with STRR. So that is 30, so it is around 25. They are not very different from each other. But I'll tell you later on, because that is purely statistics. So we will not spend much time here. Then there is this percentage of RR intervals which are different by more than 50 milliseconds. So this RR interval is say 660 milliseconds. The next RR interval is 720 milliseconds. So the difference between the two is more than 50 milliseconds, isn't it? So how many successive beats are different from each other by more than 50 milliseconds? This is also calculated here. If you have got a greater variability, this will be a high value, 10, 20, 25. If you don't have a variability, every RR interval is coming at fixed sort of thing. Then the PRR50 would be maybe 0. All right. Then we have got, this is called time domain parameters in HRV, heart rate variability. Then we have got another thing, frequency domain, where I will just mention a couple of things because again these are statistics. Low frequency, this is what we will be dealing with, where you can say the variations in heart rate are going on a smaller time scale. So if we are recording 5 minutes, say the first 10 seconds are high heart rate, 20 seconds, a low heart rate. And, so there is, you could actually plot a wave like this. So this could be a low frequency and this could be at a higher frequency. The changes are occurring at a higher rate. Then there is a ratio between these two. So here we have got say 30.83 and 12.52. And then the ratio between them 2.4. So all these things we will be dealing later on. But I hope you have got a little idea that there are variations. And all these are statistical things which will convey some message. Now what is the message? Now as I mentioned that SA node is the pacemaker.
Yes.
So whatever rate this is giving, you will have that heart rate under normal conditions. SA node is being governed by what?
Being what?
Governed, influenced.
By the autonomic nervous system.
Excellent. What are the two components?
The
Sympathetic,
sympathetic and parasympathetic.
parasympathetic. So both of them are acting on SA node. If you remove both of them, what will be your heart rate?
Whatever the SA node decides.
Yes. What is the usual heart rate that comes from SA node? Approximately.
From about 90.
Get 90, 100, something like that. So this is what is called intrinsic heart rate. If you don't have any autonomic modulation, your heart rate under normal conditions should be beating at around 100. But usually your heart rate is
Limited by the parasympathetic.
yes, this is important thing. Usually you have got a parasympathetic dominance. My heart rate remains something around 55, 60. When I go to sleep, I am on bed maybe 48, 47. This is my usual thing. Which means I have
A parasympathetic.
very strong parasympathetic dominance. We have got so many other people whose heart rate may be 100 or crossing 100. So from autonomic point of view, it means
The sympathetic system.
is dominant. In these conditions around us now, where there are so many stresses, you tend to have
Sympathetic dominance.
parasympathetic is
So less control from the parasympathetic.
it's not lost. It's a sympathetic dominance.
Yes.
Stresses, your sympathetic system is more active. So it overcomes parasympathetic. Okay? And you, of course, know that parasympathetic dominance is better. It means you are
Relaxing.
relaxing. Minimal stresses. Now, nicotine is a
Stress.
Is a stimulant.
stimulant. Okay? It may stimulate from so many other things. The preganglionic fibers, they are mostly nicotinic, whether they are sympathetic or parasympathetic. So if you have got probably more nicotine activity, so likelihood that sympathetic activity would be more. And there are some other also mechanisms. Cigarette smokers, they do have a higher pulse rate and high blood pressure, which are indicators of sympathetic dominance. Okay. Now, in these parameters, RMSSD basically is an indicator of your parasympathetic activity. If you have got a higher RMSSD, means stronger parasympathetic influence. If RMSSD levels go down, become less, 10, 15, it means the parasympathetic is
Dominate.
not dominating, down.
Okay.
Higher value RMSSD is indicator of parasympathetic
Parasympathetic
activity more. Okay? So remember RMSSD. Same goes for PRR50, more variation. If you have got parasympathetic dominance, there will be more variation. Heart rate variability will be more. So these are two primary indicators of parasympathetic activity. Higher the better. Then on the other side of frequency domain, HF, high frequency, is again similar to RMSSD. So if you have got a higher level of HF, it means parasympathetic.
Dominance. Parasympathetic.
On the contrary, LF is more in line with sympathetic. Okay?
Which one?
LF, low frequency.
Okay.
LF is more in line with sympathetic activity.
Okay.
A higher LF probably
Sympathetic dominance.
it's not as you can say reliable as HF. HF is more reliable for parasympathetic, but LF, it could be a mixture of sympathetic, parasympathetic, but a number of people, they just say that if LF is high, indicates sympathetic activity is higher.
Okay.
Now, if we calculate the ratio LF over HF, if LF is more, of course the ratio will be more.
Yes.
So LF over HF, technically in the articles they say it indicates sympathovagal balance. What?
Sympathetic.
Vagal balance. If LF is increasing, meaning balance is going in favor of sympathetic.
Sympathetic.
If the LF is decreasing and the HF is increasing, the balance is going towards
Parasympathetic.
parasympathetic. So you will have a smaller ratio. Here the ratio is 2.46. If it becomes 0.8, it means parasympathetic dominance. If it becomes 5, sympathetic.
Sympathetic.
Very clear? Now, we have got some additional thing which is called non-linear parameters. Again, this is another description, standard deviation. So this again is very related to RMSSD, ST1. So whatever is the message coming from RMSSD should be from ST1 also. So ST1 is again an indicator of parasympathetic. Okay? So this is how you get the report. Now one method of Now putting the results, you will get the report for a person. Now you will have to get the data into Excel sheet.
Okay.
Okay.
For each person.
All these values.
Yeah. Okay.
So
We
the,
got an Excel sheet for these
No, no.
vapors and other
Okay.
one for this
Mhm.
control.
Yes.
Yeah, this will make it.
so this makes an Excel sheet for one person,
Yes.
but we have to take the values manually and put them in an
Uh,
Excel sheet for
uh,
everyone.
Yeah, this is now you will have to learn a few steps. That how to minimize your manual input. There are facilities for automated things, but finally, as you mentioned, for 1% data, you will have to copy the whole of it and then put into a cumulative Excel file. So as you mentioned, you will have two files, one for the controls, or you can have a single file also. On top, there is column for controls and bottom there is this space for.
Okay.
But it is better to have two separate things. From the very beginning, actually, what you would do is in your computer, one person should be assigned to have the data, accumulated data. You have to update it. So to make two folders, of course, first folder is your vaping research folder. Then two folders, one is control, one is
Case.
cases. Then in each folder, you make a folder for every subject because you will not have one file, you will have multiple things
Code.
later on.
Code.
Okay? Case 1, case 2, case 3, case 4, case 5. So every person should have a folder for himself. Okay?
You mean a folder for each person of us or of the
Yes, each person.
participants? Okay.
No, each participant.
Participant.
You are also
You're not the
participants.
Okay. Okay.
If you are the participants, yes.
For
Okay.
each participant.
Yes. Okay. Sure.
Shabab, so to make sure that this information is cherished and used well, that you are recording, send it in the WhatsApp. Make the WhatsApp as the resource for you later. If any problem you face, go in the search and see videos, see the chat, okay? And avoid the side messages so that you don't look for other any information. Okay?
All right. Okay. So data management from the very data management from the very beginning is very critical. Otherwise, once you have got 10, 20 persons, then you just get confused what is happening. Because we will be introducing the phenometer also for BRS calculation. It needs more extensive work. Okay. All right. So now you have got an introduction to what will be the type of report. Options for making certain plots. One of the plot which is now given in the literature is called point care plot. I'm just going to show this because this is used for SD1, SD2 calculations. So what is this plot? You have got an RR interval, say 700 millisecond. Okay. The next interval is 720 milliseconds. So in this plot, this RR interval of 700 will be plotted against the next interval of 720. So for example, this is a point which is basically showing you that the first RR interval, this is RR interval, okay? That was something around say 622 millisecond. And immediately the following one RR interval, we call it RR plus 1. That was 630 milliseconds. So this is the point which is representing a relation of these two successive beats. Okay. So this is RR and this is next RR. We could say RR plus 1, the next RR. So all these points are basically like this, one after the other, the next and the next and the next. As you are sitting in the line, so first point is between these two, second point is between these two, third point is between these two, like this. Okay. This also gives you a scatter, that how much the beats are varying from each other.
Okay.
Okay.
The
So,
variation
yeah.
increasing.
So this is a graphical form. and it immediately gives, oh, it is very scattered. So without going into actual figures, you get the idea. All right, so pointer plots we will be also dealing with. Now what we can do is try to record an ECG.
Yes.
Okay? For
Let's go. Can you try it on my laptop, doctor, so I can have some information on it?
yes,
Some material?
you can close this one. Now, how to save? Yeah, this is an important thing. File, save as. My own criteria is I assigned, because most of these are students. So their ID number. So what is Isa, your ID number?
218.
Isa's, huh?
000
000
2067.
2067. So this is ID number followed by date. Today's 17 11 22.
Never forget.
Okay. So whatever criteria you decide, it should be followed. This is our criteria of naming our cases.
Okay, but I think the participants won't be students.
Yeah, you could use their mobile number, put the mobile and date,
Or their national ID. Can
or
we
their
use
national ID.
yeah?
You decide amongst yourself.
Okay.
I have given you the example that it should follow a pattern. Preferably, it should include the date.
Yes.
Okay, so that all of you understand that, oh, this is from this case number 1, 2, 3, 4, whatever it is. Okay, and then as I mentioned that it should be in a folder. Save where it has saved it in its own folder of lab chart. Okay, so we don't want that. We'll create the folder and put every file there. Okay.
Okay.
So we have done new file, we have done save file, we have done folder management. I'm going to use 3 channels here. Ultimately, we'll be using at least 4 or 5 sometimes. Channel 1, we will just make it as ECG. Okay. Channel 2 will be pulse, and channel 3 will be respiration. Okay. Now what you see here is a sample rate also. Sample rate means how many points will be recorded in a second for this signal. So for example, if we say 2 points, sample rate is 2 per second. So 1 point will be here, 1 point will be here.
So it's too low. Too low.
Yeah, too low. It will be a straight line, it will not be a wave. So you need at least maybe 100 points in a second so that you can have a wave actually, isn't it? And you should not have too many points, otherwise your file will be so big. Every point is going to take some space, data. So standard thing is 1K, well, that is 1000 points per second. For ECG, it is perfect. For respiration, we don't need that much because we just need a wave to show that, yeah, this is inspiration, this is expiration. So even if it is 100 points, that could suffice. But for
It's okay if we go up to 1,000. It's okay if we go.
yeah, it's okay. A higher rate is better than a lower one because in lower one you lose. In lower one you lose the actual waveform. It could be. All right. So this is one. Now you also see here that program automatically is detecting that there is a bioamplifier attached to the power lab. This is. Rest of the input amplifiers, their maximum signal recording is 10 volts, but bioamplifier is 100 millivolts. This one, bioamp. This one is the bioamp. So it is attached to the power lab. Signal will go through this. What is the significance of bioamplifier? It has got special safety mechanism inside it, so that the electrical current that is generated is isolated from the main currents. So it is a safety procedure, and that is an essential thing. You would see that there is a mark of heart here. This is suitable for attaching to human beings for recording of heart activity. If you don't have that mark, you must not attach that device to a human being. Okay? Must not.
But what happens if we do?
There is a danger that electrical current could pass in the reverse direction and the person.
End up in ventricle fibrillation.
Yes, especially this fibrillation, ASST, what anything could happen. Safety, as we say in this ethical guidelines, is the priority. You have asked a person, you have given him even Kapsa and Pepsi, and please come and.
Yes.
But still, it is his decision. He can stop any moment. No, I don't want to continue. Stop recording. You must stop.
Yes.
Okay? You might have spent 1,000 riyals on him. Doesn't matter. If he does not want to continue, you have to stop. It is his right.
Of course.
Okay? So again, this is protection, that if we want to have an electrical device attached, it should be safe for human beings. And this is one. In some of the other transducers or bioamplifiers, you will have a figure just like a human being, head and 2 arms and 2 legs. Okay. Now the ECG signal is a very low voltage signal. Low voltage. Low voltage means, have you seen ECG strips? Calculated the things? What was the voltage?
We didn't focus on the voltage, but we saw the strips. What about the voltage? It's going to be low. Okay.
In milli or microvolts?
Millivolts. 1, 2 millivolts, something like that, usually. That is the thing. So that's why you need an amplifier. The voltages are so low. Unless you amplify those, you will not be able to see or record. Even all other signals, this machine itself has got a couple of things, including amplifiers, some filters, so that the signal becomes clean and better for visualization. But even lower voltages, you will have to have more dedicated bioamplifiers which can perform certain other functions and give you a faithful signal.
So, Doctor, if I'm understanding this correctly, the signal is first detected here.
Yes.
These are cables for the sensors.
This is what I told them before you came, that this is an analog to digital converter.
Okay, so it collects the analog signals from the sensors and it passes them through the amplifier.
Then this converts it into a digital form.
Okay.
So that's why it is called analog to digital converter.
So if it is already digital, then why do we need this piece here?
This is basically going to feed the signal here. The signal, the ECG signal, first is going to go through this, then it will be fed to the power lab. The sequence is like this. This is the bioamplifier. Okay. And this is the signal going into power lab. From where the signal go into the bioamplifier? Through this lead. This is the ECG box. ECG box is attached with these wires. And these wires will be attached to the
leads.
So the signal starting from here, first going into this to be amplified, and this is the place which is isolated from the main electrical current. Then the signal would be fed into the power lab, and then
to be converted.
digital form into the computer.
Okay.
So, who is, you are the subject now?
Asha?
Huh?
Okay. What am I supposed to do? Shall I press on it or?
No, no. This is the respiratory belt.
Does it go in?
It's Nemo trace, okay? So as you inspire, it will be stretched. And this signal is supposed to be recorded. Okay? So you can have some access. So let's see whether we get some signal or not. Yes, you can move, don't worry. Okay. Your respiration is being recorded.
Is my pulse on now or?
We have other pulse transducer, so inshallah we'll use that one also. Yes, now it is okay.
The pulse is not going, right?
Yeah, it is.
It is?
Yeah.
It's normal?
Yeah.
But if I hit it, there will be distortion.
Yes.
Okay.
Should we encourage voluntary respiration or only involuntary? Should we tell the participants that?
We'll have
Take
both,
deep
both things.
breaths.
Yeah, deep breathing later on. Huh? Now for ECG, this is, let us see what happens. We'll have to first go to say 5 millivolts. Then we go to bioamp and mains filter. No, we're not getting the ECG up till now. Let me the usual thing about not getting ECG is not good connections. So I told you these flows are now overload. So see, it has been added
No.
here. Huh?
Yes.
Okay. Now what we'll do is we'll do deep breathing. Okay. So when I ask you to do it, you have to do it gradually. It should not be abrupt. Yeah, I have shown you, and you follow me. 1, 2, 3. Okay.
Shall I start
So-
now?
Yeah, I'll ask you now. When you are ready, okay. Go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. We'll go to the options and convert it not as general sine wave, but this is ECG human. Okay?
Yeah.
Now it will be able to detect most of the peaks automatically. And we will also do a format that we want decimals, no decimals, because this will be automatic.
So we fixed the changes we made in the beginning, right? Because it wasn't ECG then.
Yeah, now we are configuring it. Okay. Second one is pulse. Again, we use cyclic measurements. We would like to have the rate in the mini window, and this is pulse. Go to options. Again, default is general sine wave. No, we want finger pulse. Okay. Then we go to third, respiration. Again, cyclic measurements, average cycle rate we see on the window, and options we select respiratory belt. Okay. And in format we again go to fixed, no decimal required for us here. So we have got now 3 things.
Yes.
So what we do is first let us do a clean area before deep breathing. So for example here, small area. So your pulse average cycle rate 75. By ECG 73. It might have missed 1 or 2 things or in the pulse. And your respiration is 15 beats per minute, 15 breaths per minute. Okay?
Aren't I on the lower side or?
Everything is okay.
Okay.
You are perfectly normal, physiological person.
Thank you.
Okay, now we go to deep breathing. Now in deep breathing, if we select the whole, it should be very similar to what you have seen. 77. Average pulse, maybe it is missing or there are some duplicates. That's why it is. That would not be right. ECG is correct because ECG peaks are very clear. And your respiration is slow. It should be 6 basically. Now the thing to see here is,
Why is that difference between the pulse and ECG?
because of the noise there.
In that case, do we need to repeat it?
This is what is the backup. Ideally, everything should be done by ECG. Okay.
So it is only a backup. No?
Yeah, that's it. Now see here, it is 83 beats per minute during your inspiration. Okay. And during your expiration, it's 73.
Yes.
So this is what is in physiological terms, this is called sinus arrhythmia. As you inspire, your heart rate becomes faster. As you expire, the heart rate becomes slow. So this is arrhythmia, but this is sinus arrhythmia because this variation is coming from sinus node. As you inspire, the parasympathetic dominance is more or less.
More.
No, less.
Less.
Heart rate is getting faster.
Right.
And as you
And the
expire,
opposite. Yeah.
opposite. Okay. So this is
So when I inspire, the heart rate is up, goes faster.
okay. So this is a variation that should be present. If it is not present, means your autonomic control is
Has issues. Yes.
in what condition it could be there.
autonomic control. For example, diabetic patients.
Excellent. Huh? So there will be a demyelination, etc. So autonomic neuropathy is there. So the person may not show any variation.
Yes.
Inspiration, expiration, just the same. Okay. All right. So just remember that average heart rate, your average heart rate is something around 77. Now we go to Valsalva maneuver. This is Valsalvas. Okay. So it is going to 92. Pulse is
I started moving my finger, maybe that's why.
91, and after Valsalva 76. These are the areas where the pulse rate really goes high, but because the ECG is also noisy here, so we are not looking at it very clearly. Even the blood pressure, it goes very high for a short period and dips down. So we'll do it inshallah later on again.
Okay.
But I've given you an overall thing and the protocol, then you can release him now. Start taking off the things.